Without a doubt, it's one of the most astounding natural phenomena on the planet. One look at the Northern Lights, and you instantly understand why ancient cultures believed they were magical. And even today, in our scientific age, researchers still don't agree exactly how this planetary light show works.
When I first saw the aurora up in Fairbanks, Alaska, one of the most striking features I saw about it was I looked at it and said, wow, that's the Earth's magnetic field painted in light.
Dr. John Bonnell is a research scientist at UC Berkeley's Space Sciences Laboratory. He's a key member of the team behind a recently launched space mission called Themis. The mission's goal is to study the exact cause of the Northern Lights.
The manifestation of it here down on the Earth is the aurora borealis, and it is a manifestation of the electrical activity that occurs due to the interaction between the solar wind and the Earth's magnetic field.
Although most of us aren't aware of it, the Earth is under continual bombardment by an unseen stream of particles from the sun.
It is very definitely a wind. It flows at several hundred kilometers per second off of the sun, and it flows past the obstacle that the Earth's magnetic field presents to it at speeds that are essentially supersonic.
Without serious shielding from this solar onslaught, the Earth would be a much less hospitable place. Luckily, we're protected by a natural force, the Earth's magnetic field. But the Earth's magnetic field pays a price for its exposure.
When the solar wind blows across the Earth's magnetic field, folding it back to form this long tail that is the tail of the magnetosphere, or the magnetotail, it drives electric currents that flow along the magnetic field lines. What's happening when you fold back the magnetic field and make this long tail, you're storing a lot of energy in that field configuration. A lot of energy is being transformed from the flow of the solar wind into this sort of stacked up magnetic field. And it's that reservoir of energy that is tapped into in a magnetic substorm.
Magnetic substorms are violent disturbances that occur in the magnetotail, often over 20,000 miles from Earth. And thanks to the Earth's magnetic field, the disturbances are literally broadcast onto the night sky at the Earth's poles.
In essence, the Earth's atmosphere is acting as the phosphor on the television screen and providing, this image spread out over the northern latitudes of what's going on. It's like a funhouse mirror because the Earth's magnetic field is pulled out into this long tail and stretched and twisted and sheared. And so it does take a lot of interpretation to understand roughly what's going on. And in addition, it requires in situ measurements.
Although casual observers may be content to enjoy this spectacular show, space scientists like Dr. Vasilis Angelopoulos are interested in understanding the exact nature of the magnetic substorms that cause the auroras. Their aim is to predict substorms so they can warn astronauts and keep satellites safe.
This problem is fundamental enough, yet it has been unsolved for 30 years now.
Starting in 1993, Dr. Angelopoulos began formulating the idea for a multi-satellite mission that would finally lay the substorm mystery to rest. After multiple attempts to get NASA funding, in 2002, his Themis mission finally got the green light.
What the beauty of Themis has been is that not only does it address a key scientific question in the field, but it does so in an economical way. We designed a mission that would take 5 identical satellites and put them on the same rocket and then put them out in space in a common initial injection orbit. And from then on, we would use their onboard propulsion on the individual satellites to put them in their final positions.
For the duration of the 2-year Themis mission, Angelopoulos' team in Berkeley will be responsible for all aspects of the project. One of the most interesting tasks was the actual design and testing of the magnetic and electric field sensing instruments. The Themis team also constructed and currently operates the Mission Control Facility, which is based in Berkeley. From here, they've been controlling all 5 Themis satellites since their initial launch from Cape Canaveral, Florida, in February of 2007. Dr. Manfred Bester is the Themis Mission Operations Manager. He supervises all phases of spacecraft control and communication.
In the front row, what you see are these mission control consoles where the flight controllers sit and where they communicate with the spacecraft. Communicating means you establish a radio link between the spacecraft and one of our ground stations, and then that gives us the opportunity to send commands to a spacecraft and to receive telemetry data, which contain the science data that we acquire with our instruments, but also so-called state of health information, such as temperatures or battery voltages, currents.
The complexity of the tasks managed by Dr. Bester and his team is compounded by the fact that all 5 Themis satellites have to be aligned into very different orbits. It's the only way they'll be able to measure the development of magnetic field substorms with a high degree of accuracy.
The innermost satellites have a period of 1 day. They take 1 day to go around the Earth. The next one out would have a period of 2 days, and the final one a period of 4 days. This allows us to line up the satellite once every 4 days along the Sun-Earth line. They will be perfectly positioned to determine whether that energy flow is from the outside in or from the inside out. The field of space physics has been around for 30 or 40 years now, but it's still in its infancy in terms of understanding and predicting the space weather that surrounds us and that immerses the satellites and astronauts that are flying out there. The analogy that I give is that we are in space weather today where atmospheric weather was about 100 years ago, when with the advent of telegraphy and multiple stations all around the continent, we were able to put together a picture of how weather fronts move from one to the other. It is very important for us to understand and predict how these substorms take place and when they take place, because they're parts of larger space storms that affect telecommunication satellites and astronauts.